Hello, class. This lab introduces the key characteristics of igneous rocks and how we identify them using texture, composition, and visual observations. First, let's do a quick review from the previous lab. Earth's crust is made up of layers with different densities. Continental crust is less dense than oceanic crust, while deeper layers like the mantle and core are even denser. Oceanic crust is primarily composed of mafic minerals, which are dark, dense, and rich in magnesium and iron. Continental crust, on the other hand, is mostly felsic minerals, which are lighter, less dense, and rich in silica. At subduction zones, the denser mafic crust sinks beneath the lighter felsic crust. Remember what counts as a mineral. A mineral is an inorganic, naturally occurring solid with a crystalline structure, has a characteristic chemical composition, and distinctive physical properties. Now, remember, are rocks and minerals the same thing? No. A mineral is a pure substance, whereas a rock is an aggregate made up of one or more minerals. You can think of it as a hierarchy. Atoms form elements, elements form minerals, and minerals combine to form rocks. Now, some ways to identify minerals are by looking at its crystal habits, color, streak, luster, cleavage or fracture, and sometimes they have special properties such as taste, smell, fluorescence, magnetism, etc. Remember, color isn't always a reliable way to identify specific minerals, but it can help when classifying igneous rocks. Felsic rocks tend to be lighter in color, while mafic rocks are generally darker. There are also intermediate rocks which fall between the two and can be harder to identify based on color alone. Let's talk about what kinds of minerals are commonly found in igneous rocks. Quartz and feldspar are dominant minerals in felsic igneous rocks, while olivine, pyroxene, and amphibole are common in mafic igneous rocks. Mica can appear in both felsic and mafic compositions. Igneous rocks are formed by the solidification of cooled magma or lava because of volcanic activity in areas such as hotspots, and can later become sedimentary or metamorphic rocks through Earth's dynamic processes. Igneous rocks can be broadly classified as either extrusive, volcanic, or intrusive, plutonic. Extrusive rocks are extruded from the Earth's surface and cool quickly due to exposure to the surface and air. Intrusive rocks form in the pluton or magma chambers and cool much slower. The differences in how extrusive and intrusive rock cool give the igneous rocks different textures. The texture and composition of the igneous rock is how they are classified. Keep in mind, the cooling rate affects the texture, not the composition. Extrusive rocks form from lava that cools quickly at the surface, forming small, fine-grained or glassy textures. Intrusive rocks form from magma that cools slowly underground and form large, coarse-grained textures. Here are some of the common textures used to describe both extrusive and intrusive igneous rocks. For example, extrusive textures can be defined as amphitic, glassy, vesicular, or pyroclastic, and intrusive can be described as phaneritic or pegmatic. There's also another one called porphyritic that we will discuss a bit later. Now we'll go over all the textures in a bit more detail, starting with the 4 extrusive textures. Amphitic texture refers to fine-grained igneous rocks that form when lava cools rapidly at the surface. Because the cooling happens so quickly, the crystals don't have time to grow and are too small to see with the naked eye. Common examples include basalt and rhyolite. Glassy texture forms when lava cools extremely rapidly, usually in high silica content lava. Because the cooling is so fast, no visible crystals can form. Obsidian is a classic example. It's important to remember that glass is not a mineral. This rock simply cooled so rapidly that the crystals could not form. Also, obsidian is considered felsic because it is made almost entirely of silica, even though it appears to be dark. Vesicular texture forms when gas bubbles escape from lava as it cools rapidly, leaving behind cavities in the rock. Common examples include pumice, which is felsic, and scoria, which is mafic. Finally, we have pyroclastic texture, which is a composite of various volcanic material that was ejected during an eruption. These pyroclasts can be composed of pumice and scoria, volcanic ash, and tuff. Phaneritic texture refers to intrusive, coarse-grained igneous rocks that form when magma cools slowly underground. This slow cooling allows large crystals to grow, making them easily visible to the naked eye. Common examples include granite and gabbro. Pegmatic texture forms when magma cools very slowly, allowing exceptionally large crystals to develop. This often happens in water-rich environments where fluids help minerals grow rapidly. Pegmatites are also known for containing rare minerals. Now, the porphyritic texture forms when a rock begins cooling slowly, allowing large crystals to develop, but is then an event causes the partially crystallized magma to be erupted to the surface. The remaining molten material cools rapidly, forming an amphiritic or fine-grained matrix surrounding the earlier phaneritic or coarse-grained crystals. Now we can use a composition color index that help us tell the differences between mafic and felsic rocks. Felsic rocks are generally light-colored, silica-rich rocks with minerals like quartz and feldspar dominating, and they contain only about 15% of mafic rocks. Intermediate rocks have a gray to salt and pepper appearance and contain about 16 to 45% mafic composition. Mafic rocks are dark, iron and magnesium-rich rocks, often black or dark green due to minerals like pyroxene and olivine, and they contain 46 to 85% mafic composition. Ultramafic rocks are very dark and often greenish, reflecting their extremely high olivine and pyroxene content with more than 85% mafic minerals. This is an example of how the percentage of mafic minerals in a rock can influence its appearance. As the mafic content increases, the overall color of the rock becomes progressively darker. Chemistry differences in igneous rocks influences their color, mineral content, and melting behavior. Silica-rich rocks tend to be lighter in color and have a lower melting temperature, while iron and magnesium-rich rocks are darker and melt at higher temperatures. These chemical variations also affect where the rocks form and how they behave during volcanic eruptions. During this lab, you'll identify igneous rocks using visual observations. Start by estimating the percentage of mafic minerals in each specimen. You can do this by assessing how light or dark the rock appears and matching it to the color index. Next, examine the rock's texture to determine whether it is coarse-grained or fine-grained. This step helps you determine whether the rock is intrusive or extrusive. Once you know both the mafic percentage and the texture, find where those two characteristics intersect on the classification chart. That intersection will give you the correct igneous rock name. For example, we identified the rock as intermediate on the color index and noted a porphyritic texture. Together, these characteristics indicate the rock as andesite. This chart uses the same classification system as the previous one. It's simply formatted a bit differently, mainly in how the color index is displayed. You're welcome to use this version if you find it easier to read. You likely won't need to use this final chart, but it's available if you do. It simply illustrates how to classify igneous rocks using the color index, what characteristics to look for in specific minerals, and how to recognize different textures. If you have any questions, review the lecture and slides first before reaching out. And as always, good luck.